Hello and welcome everybody. This is Noah, and in this video we're going to look at an application of distance, speed, and time that can work out to be a rational equation that we can solve to find an answer to a particular given scenario here. Let's go ahead and take a look at the example we're going to use. We have a boat traveling from town A downriver 90 miles to town B. Just go ahead and start by drawing. We have town A, go downriver to town B. Let's note a couple of things here. This is 90 miles, and let's note that the current is going this way from A to B, right, because we're going downriver. We stay overnight and then travel back to town A, this time fighting against the current, right? And it's again 90 miles. And this takes 4 hours longer. Than the trip from A to B. Oops, from A to B. There we go. And let's see. And the reason that it takes 4 hours longer is because it was fighting now a 3 mile per hour current. So now we're being told what that current's speed was. That's 3 miles per hour in that direction. So when we're going down from A to B, the speed of our boat's going to be helped by the current, right? It's going to be sped up by that current. And then on the way back, it's going to be hindered, slowed down by that current. So suppose the boat used a constant motor speed, right? So you just set the engine on whatever it is, and we want to determine the boat's still water speed. So the first thing that we always do, super important, is going to be define a variable for what we're trying to find, or what we are looking for. So in this case, we'll say let V equal the boat's still water speed. That's what we are looking for. All right, for these specific kinds of problems, we're going to use the fact that time of travel equals the distance traveled divided by the speed. And the other thing that we're going to use is that the times between the two scenarios are related. Right, so each scenario we are going a different speed because the current's helping or hindering us. But those times are related by that 4 hours, right? It takes 4 hours longer for the second trip than it did for the first trip. 4 hours longer when we're fighting the current than when we're going with the current. So let's start, now that we've got our variable defined, let's find the time. I'll say T1 for the trip from A to B where we're going with the current. So the distance is 90 miles, and the speed is going to be V, our still water speed, right? We have the engine set to a given still water speed for both the trip there and back, same engine setting both ways. When we're going with the current, that current of 3 miles an hour is going to be helping us. So we can add that 3 miles an hour to the speed we would be going in still water. And so this will be the time it takes us, right? This will be the time it takes us to get from A to B, depending on what we set our, the speed of the boat to be. And then on the way back, I'll call this T2. The distance is the same, 90 miles, but this is going to be over V minus 3. And the reason it's going to be subtracting 3 is because now the river is fighting against us. It's going to take away 3 miles per hour from the speed that we would be going in still water. All right, so that's step number 2. And I do want to go into number 3, but we've kind of done this formulaic, like, okay, use this formula. Where does this formula come from? It's easiest explained in the opposite direction, that distance equals speed times time. Speed multiplied by time. And to show an example, we could do, like, if we were going 60 miles per 1 hour, 60 miles an hour, down the freeway, and we were driving for, say, 2 hours. Well, we went 60 miles in the first hour, and then 60 miles again in the second hour, for a total of 120 miles, right? So if we take speed and multiply by time, then we get how far we've gone. If I divide the speed to the other side, then I'll have distance over speed equals time. So that's where that formula is coming from. It's not just some magic formula. That really does make sense in context of how everything's working. So that's the formula we use to just set up some equations for both of those. We don't know what those times are because we don't know what how fast the boat would be going in still water. But now we can move on to step 3, where we look at how those times are related. The second time is 4 hours longer than it was for the first time. So if I take and add 4 hours to the first time, that will be how long it takes for the trip back, right? Take that first time, 4 hours longer than that, plus 4 to get this amount of time that we take to get back. Now that we do this, then we can plug the equations from step 2 into the equation in step 3. So we'll have the 90 over v plus 3, bring down the plus 4, equals the 90 over v minus 3 for T2. And now we have an equation with just v, which is the speed of the boat in still water that we're looking for. So if we solve this equation, we'll have our answer. We'll have the value of v that we set out to find in the beginning. So we can multiply both sides by the common denominator, as we have been in these problems, which is v plus 3 times v minus 3. And on the left side, v plus 3 times v minus 3 times 90 over v plus 3 plus 4. We need to take the v plus 3, v minus 3, and distribute it over the addition to both terms, the 90 over v plus 3 and the positive 4. So I'll write that out now. We've got v plus 3 times v minus 3, and this first multiplies by the 90 over v plus 3. We go plus 4 times v plus 3 times v minus 3. And then this equals, on the right side there's no distribution, but we can cancel the v minus 3's. So we'll have 90 times v plus 3 here. And so we've cleared out our denominators. On the left side, we have v plus 3 times v minus 3 times 90 over v plus 3. The v plus 3's can cancel, leaving us with v minus 3 times 90. And then in the second term, we have the plus 4 times v plus 3 times v minus 3. We'll FOIL out the v plus 3, v minus 3. That's going to be a difference of squares, v squared minus 9. The middle terms will cancel as a plus 3v and a minus 3v there. We can bring down the equal sign and then distribute the 90 on the right side. 90 times v plus 3 becomes 90v plus 270. Great. Now on the left side, we have v minus 3 times 90 for our first term, and we'll distribute the 90 to get 90v minus 270. and then plus our second term, 4 times v squared minus 9. Distribute the 4 to get 4v squared minus 36. And on the right side, nothing to do there. We'll just bring that down. Now I've got bells going off in my head because I see a v squared term and a v term, so I want to get everything to one side. I'll subtract 90v from both sides. That'll be nice. It'll cancel there with the other 90v. And I'll also subtract the 270 from both sides. Now what I'll get is negative 540 with the 270s plus 4v squared minus 36 equals 0. And then we can combine like terms here to get 4v squared minus 576, it looks like, equals 0. And then there's no more v terms, so I can actually solve this without factoring. I can add the 576 to the other side and then divide by 4. Does 4 go into 576? It does, because 76 is 4 less than 80. So let's figure that out. 4 goes into, let's just do long division. 4 goes into 576. I could do this. 4 goes into 125 times, and we have 500s. And so we can kind of work it out that way and then figure out 4 goes into 80, 20 times it goes into 76, 19 times we kind of work those through. But I think for this right now, as we look at this, we'll do long division. 4 goes into 576. 1 times 4 is 4. Subtract, we get 17. Bring down the 7. So then 4 goes into 17 4 times. 4 times 4 is 16. Subtract, bring that 1 down, and then bring the 6 down, and then 4 again. So this is 144 after dividing by 4. Then we can take the square root and get v equals plus or minus. The square root of 144 is 12. And we only care about the positive answer. We're not going to be driving the boat backwards, per se. So we can finally conclude, put this as a step, state a conclusion using a complete sentence. All right, so we can now say that I want to mention the scenario that we're in as I state my conclusion, so I want to think back about this. Okay. I'll say if the trip back takes 4 hours longer, if the 90-mile trip, we'll be specific here, 90-mile trip back takes 4 hours longer than the 90-mile trip with the current, with the 3-mile-per-hour current. These are all of the conditions we needed for this problem. Then the boat must have been set at 12 miles per hour in still water. Right. Its engine was set in such a way that it would have been going 12 miles an hour in still water. Now, if we think about that, that means that on the way down, it was going 15 miles an hour because the river was helping it by 3 miles an hour, and on the way back, it was going 9 miles an hour because the river was hindering it. All right, and that's our final answer. That's it for this. So keep in mind these steps, have these notes with you as you now look at the next problem, the Now You Try problem, and work through that one. All right, thank you so much for watching, and we will go over that solution to the Now You Try problem in the next video. See you soon.